So I will need to stop the recording over here for a minute because my okay. So we just earlier talked about the fact. Meher, you have a question? Your hand is raised.
Oh no, sorry, sir. I forgot to do it.
Yeah. So we were just talking about the fact that due to band bending in the semiconductor region, the MOSFET capacitor would behave different. The MOS capacitor would behave differently than a metal capacitor, a metal oxide metal capacitor. So to be able to characterize this, what we do is we apply a voltage between substrate and the gate, and we say that we will vary this voltage V, and we want to observe the the change in charge and the change in capacitance or the flow of current that is happening to measure the capacitance there. Okay, and you see what happens over time when I apply negative voltage on the gate. What would happen when I apply a negative voltage on the gate? Though this is a p-type substrate, more holes would accumulate at the surface of silicon. Are you able to see this?
Yes, sir. Yes, sir.
Huh?
Yes, sir. Yes, sir.
So this part is called accumulation. Now, when I say that I reduce that negative voltage, I bring the voltage closer to zero. Then what happens? Then we looked at this band bending diagram when this voltage at both the nodes was zero. So I would have this kind of a band bending happening there. So if you look at it carefully, what we are talking about it is that at the surface of the silicon over here, my EF is kind of coinciding with the Fermi level. So what I would say is that there is some, so when it is at the Fermi level, what does that mean? That the silicon behavior in this region would be something like intrinsic silicon. Are you able to see this?
Sir, I didn't understand. Can you?
So if EF is equal to EI, we call it as intrinsic silicon, that nothing is doped. There is no doping. Am I right?
Yes, sir.
Over here, if you look at it carefully, see, EI would be something like this over here in the center of EF and EC. EF and EC, EV and EC.
So EI is the band cap of silicon, right? I mean,
no, EI is the intrinsic energy level, which is in the center of EV and EC.
Intrinsic energy, okay.
EI, the red one that I'm showing, that's called EI.
Okay.
Okay. So over here, we see that EI and EF are almost coinciding due to band bending.
Right.
So I have intrinsic silicon. So I would say things are almost depleted there. Okay. And what happens is that in this region, no, if I change the voltage by a small value, a few millivolts here and there, there will be no charge change over here at the surface. The charge would change at the boundary of this depletion layer. There will be slightly extra bending or slightly lesser bending. Okay, because at the surface, it is almost intrinsic now. Any change, any more charge or any less charge, the change would happen at the boundary of the depletion layer.
Okay. Sir, so just to like clarify, so can you go back to the previous slide? This one. No, okay. I meant that yeah, this one. So here near the surface of, I mean near the boundary of your silicon and your silicon dioxide, your intrinsic energy level is coinciding with the Fermi level. So there it behaves like intrinsic silicon. So there's not much accumulation over there. But when you go away from the boundary, it it approaches the conduction.
Yeah, you start to get more charges.
So that there it behaves more like an N type. That's
P type.
so
Over
if
here,
it,
it's P type.
yeah, but sir, if it's if your intrinsic level is closer to the conduction band, then
Intrinsic level is always in the center.
okay.
So when the bands bend, intrinsic level also is shown to be bending. It is also a notional level.
Right. So yeah, so there if it's like regular P type, then why do we see a depletion region over there?
Depletion means there are no, like, if you need charges, more charges, there are not many charges available here because it's almost intrinsic.
Okay. So like relatively it's
Yeah,
relative, I mean compared to the other one, it's like N type, even though it's just intrinsic silicon.
yeah.
Okay. Right.
Okay. So what happens, because there are no charges in this region, any charges you need, you will get them from the remaining depth of the silicon. Okay. So any change in charge density would happen at the boundary of my bending. So my effective dielectric thickness, see, when we say that my dielectric, there are these two, metal 1, metal 2, and there is this dielectric in between. We say that the capacitance is equal to epsilon by A, let us say. Okay, epsilon into epsilon A by Tox. As Tox reduces, your capacitance increases. Okay? So what are we saying over here? We are saying that my Tox, we are saying that this is my capacitor because I change a small voltage over here. There is a small change in capacitance right after Tox. But in silicon, we are saying that that change in charge happens at Tox plus WD. So what happens? The denominator becomes Tox plus WD. What does that mean? That my capacitance would reduce.
Right. Okay, sir.
Okay.
Because
Now,
then it's effectively a capacitor with in series with another. So it's
yes.
right.
Then if I do still more, apply still more voltage over there, then there will be still more band bending. Still more band bending would mean, let us say this, and this would mean that I had a P type, but in this region, I have an N type material now, because my Fermi level is very close to the conduction band because of so high band bending. Okay. So this is called as inversion layer. And now if I want to change any charge, there is so many charged particles available over here. All that movement of charge can happen from the inversion layer itself. So again, my oxide thickness comes out to be Tox. Okay. So when you increase the voltage over here like this, you see that initially the capacitance is high. Why is it high? It is high because the change in charge is happening across the oxide only. This is the accumulation region. After some time, we see that, oh, this capacitance starts to decrease. Why does it start to decrease? Because this depletion layer starts to get formed. And this depletion layer means there are no available charges there, so that any change in charge would happen at the boundary of the depletion layer. But all of a sudden, what happens? An inversion layer is formed. And additional change of charge happens at the surface of, or at the interface of silicon and silicon dioxide again. So this is the low frequency transfer characteristic or characteristic of the MOS capacitor. Now, why did I say low frequency?
Sir, maybe because at low frequency only that interface would be changing. At higher frequencies,
Yeah. So
that will remain there only.
At low frequency, what happens is, let us say this is the band bending thing happening there. So at low frequencies, what happens is, I have sufficient time to move electrons from here to substrate. Sufficient time to do that. And therefore, any change in electron density would happen at this interface. At very high frequency, what happens is, if I'm moving very fast, so what happens is, electron starts to go out, but it has not even crossed the depletion region when the polarity has changed. So the electrons of this region remain here only. So where does any change in electrons happen? It happens at the depletion width boundary again. And therefore, at very high frequencies, the MOS capacitance will behave as a very less capacitance.
Sir?
Yes?
Sir, could you explain this inversion layer again, sir?
Inversion layer. What do you understand by inversion layer till now?
Sir, I'm like, what I understood is that there is another layer which is being formed in between like depletion and this layer.
Oh, okay.
Yeah.
So, see, we had a p-type silicon. Am I right?
Yes, sir.
Now, due to band bending, the surface of the silicon has more density of electrons now. Due to band bending.
Yes, sir.
So that at the surface, it has now become n-type.
Okay, sir. Yes, sir. Yes.
That is why it is called inversion, because the polarity of the material, we had physically a p-type material, but at the surface, we now have an n-type material.
Okay.
That is why it is called inversion layer.
Sir, I mean, even in depletion region also, we do have these electrons, right, sir? For suppose.
No, you do not have that kind of a density of electrons as you would have in an n-type material. Depletion region actually is kind of depleted of any moving carriers. That is why it is called depletion region.
Okay, I mean, like due to this high voltage or something, we are getting free electrons in that region.
Yes.
Okay, sir. Thank you, sir.
Because so much band bending has happened, electrons can very easily come there. Okay, Rajneesh, you have a question?
Sir, can you tell the difference between EI and EF again, sir? Sorry.
So EI is always designed or always shown as the center of band gap.
Sir, it is a constant value.
EI is a notional number or a notional energy level where no electron can sit there, but it is shown as the center of the band gap. It is an energy level which is equidistant from the valence band and the conduction band, both.
Okay, sir.
EF, on the other hand, is derived from Fermi direct statistics, which says that probability of electrons above this is 50% and below this is also 50%. EF is also a notional energy level. EF पे भी कोई electrons हो जरूरी नहीं है. It is also a notional energy level. However, EF will be different. EF will be closer to the conduction band in n-type material and valence band in p-type material. EI will always be equidistant from both.
Now understood.
Okay.
Sir.
Yes, Vaishnav.
Sir, yeah, sir. Actually, when this inversion layer forms, sir, are the depletion electrons even present, sir? I mean, like below them.
Depletion has no moving carriers.
Yeah, sir. I was asking only about the layer, sir, not the electrons or the carriers. Is that present over there?
Depletion layer is always there. There are silicon atoms there, right?
Yes, sir. I mean, like
but
so
there is
there is
a flood of electrons also there. Therefore, we call it inversion layer.
So where are these electrons actually moving from, sir? I mean, like our voltage is being given between the gate and the body, to be precise. Right, sir. So where are these electrons exactly moving, sir? So if the depletion region is in between gate and body, and over there, if the over that, if the inversion laying is being formed, then I don't see any charge transfer or something, or the current transfer between the gate and the body.
The gate and the body do not have any charge transfer. A capacitor does not allow charge to move from gate to from one terminal to the other. It cannot happen, can it? There is a silicon dioxide barrier in between. Nothing would ever move from gate to the body.
Okay.
That is why we have silicon dioxide, is it not? That is
Yes,
the
sir.
meaning of a capacitor. Now, the two plates are not physically connected, but they are influencing each other's behavior. What is happening? I change something on the gate, the behavior on the silicon side changes. That is what a capacitance is.
Okay, sir, we are only talking about the capacitance value. That's it. Not about any current flow or something. Yeah. Thank you, sir.
So this high frequency model, sir, I couldn't get it. So this.
Yeah. So the high frequency model, Raghav, is about the fact that, see, it takes some picoseconds, even if it is picoseconds, for an electron to move out from the inversion layer to the substrate, to the body. Now, if I'm operating at a small signal level, which is say 20 gigahertz, how much time do I have? Just a few picoseconds. The electron may not be able to physically move out from the inversion layer to the body, but some voltage change is happening. So some charge change is happening somewhere. It cannot happen, if it is not happening in the inversion layer, it can only happen at the boundary of the depletion layer.
So like when I've crossed the VT voltage, I have my inversion layer formed. So now I can see effective capacitance thickness of Tox. Now, if I increase beyond VT, now, but still I will have that inversion layer, right?
Yeah.
So, sir, I mean, I can understand that why that like I should go up like that, because even if I'm changing very fast, even the very frequency is very fast, but still that inversion layer exists. So that Tox is constant. So what additional charge you're talking about?
So. What is a capacitance? We discussed that a little while back. A capacitance is about, or the thickness of oxide or whatever we talk about, is about, there is one plate, there is another plate. I change something here, something changes on this plate. That is the effective spacing between the two plates, is it not? Now there is this inversion layer here, fine, but nothing is changing there because there is no time for it to change. Only change is happening here only, at the edge of the depletion boundary. So this is my effective capacitance.
Okay, so inversion layer capacitance will be there, but additional to that at the depletion end also.
No, at very high frequency, inversion layer does not have any influence on capacitance because it cannot change any charges. The charges in the inversion layer cannot change.
Yes, sir.
In response to the change in gate voltage.
Okay, and so, but still, why it is getting constant then after that at the high frequency model? Shouldn't there be some kind of
depletion width cannot grow beyond a particular maximum level. Any further voltage you apply, there will be more charges in the inversion layer. Depletion width cannot go beyond that.
Okay, so after in the high frequency model, the changes in charge, the delta Q is happening at the very
at the WD max, depletion width max.
Okay. So it becomes, so this inversion becomes a constant basically.
Yes.
Okay.
Sir.
Meher?
Yeah, so sorry. So yeah, I had a question regarding depletion layer only. So like when we are going from your depletion region to your inversion region, so like it's accumulation of like effectively free electrons is just happening on the boundary, right? But as it happens, so somewhere between the inversion layer to your body, there has to be a depletion layer, right? It, so
The
yeah,
depletion layer, so the depletion layer would always be there. But at low frequency, the charges in the inversion layer can change.
okay.
Therefore, the effective capacitance that you see increases because the T-ox changes, or the effective distance between the two plates where charges are changing reduces.
Right, right. Okay.
Sir.
Yes.
Sir, my doubt was the same. I'm like this is an addition to the previous question asked by Meher. So, sir, can I think that this inversion layer which is formed, can I think that as a metal layer, and the capacitance which we are mentioning in this at the inversion point is the capacitance between the gate and the inversion layer?
Yes.
Yes, right, sir. So, and one more thing, sir. So, what about the? I'm like this question was asked by Meher even. So, what about the capacitance between the inversion layer and the body?
They are connected. Any charge can flow from inversion layer to the body. So how can there be a capacitance between them?
But there would be a depletion region in between them, right, sir?
Depletion region doesn't mean charges cannot flow from there. Depletion region only means there are no charges available there.
Oh, so even there's no capacitance between them.
Yeah.
Okay, sir. Thank you, sir.
Teja?
Sir, in that case, we can call it as a depletion capacitance is also there.
I'm sorry?
Depletion. We can call it as a depletion capacitance.
Which?
We have metal oxide, and there is a channel, and below that there is a depletion. No, sir. We can call this. Wait, one second. We can call this as a depletion, and the channel and the substrate as a depletion capacitance.
Yeah. So you see, we are calling it depletion capacitance over here. You're absolutely right.
Okay, sir. After forming the channel, also we can say that a gate and gate oxide and channel as one capacitance, and the channel depletion region and the substrate as another capacitance. So they are in the series, no, sir?
Yeah. But the change in charge is happening over here. At low frequency, change in charge happens over here. At high frequency, change in charge happens over here. So at low frequency, the capacitance is large. At high frequency, capacitance goes down.
Sir, even in the low frequency also, the depletion region will be there only.
It will be there.
Then
but no. Wait.
capacitance.
Let there be a capacitance. What would you observe at the gate? You change something. At what place will you see the change in charge? That defines the thickness that you need to consider when you measure capacitance.
Okay, sir, got it.
Okay, physically those exist, doesn't matter.
Okay.
But that doesn't come into the electrical plane, so it doesn't matter. It doesn't change anything for you.
Yes.
Okay.
Yes, sir.
Yeah, I think we can cover only till here today, but anything else?
Sir, question on this slide only. Sir,
Yes.
You have written on the upper part that MOS transistor CV at any frequency. So basically, it won't have this high frequency effect if I have a transistor. Right?
Yes. So that is evident in the previous slide. So if there is a source or drain region over here, the electrons will simply change from here to here. They don't have to travel the width of the depletion layer. Okay.
Sir, one more question.
Yes.
Sir, about the depletion, I mean, if I want to understand that, then can we say that okay, when the depletion is happening, so at the time when the band bending happens, so basically the holes move away from the interface that we were saying, surface of that, and then the ions are only there, so they cannot conduct, right? So
yeah,
okay,
that is what depletion layer is. Okay.
In the graph slide, what is quasi static CV? quasi-static CV?
Quasi-static CV means that this is dynamic in nature, in the sense that it appears as a constant CV, like constant CV curve. But what happens is that there is a constant change or flow of electrons between source drain and this inversion layer or stuff like that. So it's quasi-static. It's not, as soon as you will change the charge, as soon as you will remove the voltages, there is no capacitance there again. See, metal oxide metal, this capacitance is always there, whether there is a charge available, whether you apply a voltage there or not.
Yes, sir.
But in a MOSFET, the capacitance and its value is quasi-static. It depends on the region of operation.
Yeah, okay. The
That is what
accumulation,
quasi-static means.
inversion, right?
Yeah, yeah.
Okay, okay, sir.
So it is not a static CV. It is quasi-static. It changes with the region of operation.
Quasi-static CV.
Yeah.
Okay, okay.
Sir.
Yes.
So the question Gagandeep asked at NEF, so can you please elaborate? I couldn't get it when he asked that at NEF, at any frequency in the top part on
for MOSFET, the charges can come from the source and drain region. The distance between source drain region and that of the body is very different. So in MOSFET, even at high frequencies, you will see a high capacitance after inversion layer is formed, because inversion layer still continues to change in terms of amount of charge.
Okay.
However, in a MOS capacitor, that doesn't happen.
Okay, so that NEF was for MOSFET basically.
MOSFET.
Okay.
Okay. Teja, you have a question? Your hand is raised.
No, sir.
Okay. So if there are no more questions, we will close it here. Yes.
So depletion reason start from the flat band voltage and go up to the threshold voltage, according to this figure.
Yes.
So in the flat band voltage, there is no band bending occurs after that.
In the flat band voltage, there is no band bending because everything is flat.
Yeah.
Then
So
the band bending starts.
So after that, band bending start again in the reverse direction of accumulation.
Yeah.
Okay.
Sir, hello. Sir, just to confirm that when we are talking about the frequency, we are ensuring that the basic offset of VT is there, and about that only the frequency of the signal above that is varied.
Yeah, we're talking about small signal models over here.
Okay, sir.
Devjit?
Sir, just one question, sir. How the band bending determines my VT of the device would be?
Okay, so let us say the intrinsic band bending is 500 millivolts.
Okay. Yes, sir.
So if 500 millivolts, so at 0 volts, if I say I have already reached, let us look at it like this. At 0 volts, there is some band bending that is already happening. To create the inversion layer, I need to apply some more voltage and I will get it. Now, if my curve was such that flat band happened till here and then band bending happened like this, then the VT would come here, somewhere here.
Okay.
So the more the band bending that already happens because of my gate dielectric interface, whatever, okay? The more band bending that already happens, the lesser the VT would be.
Sir,
because I need lesser bending for bringing in the inversion layer.
Okay. Sir, from this, what you have told, can we say that if there is more band bending, then we'll be at resting state, we'll be further away from the VT. So for those type of devices, VT would be less.
No.
Sorry, the leakage would be less.
No. If band bending is more already, it means inversion layer is easy to form. So VT is going to be less.
Yes, sir.
So VT is going to be less, subthreshold leakage will be higher.
More. Okay. Yes, sir. Understood.
Okay. Anything else? Okay. So thank you guys. We will start with MOS transistors next class, and then we will move to other devices. Okay.
Sir,
thank you.
Sir, one doubt.
Yes.
Sir, in Devjit's question, sir, we told that VT is less, then how we told that it is in the sub threshold?
I'm sorry.
Sir, sir, you told no, that in more the back bending, the VT gets lesser. Sir, how we determine that it is in the sub threshold, sir?
Oh, that's because at lower VT, when you have less VT, then the sub-threshold currents are higher. That's the only thing. Oh, don't worry about it. We will talk about the current. If you've studied current equations of MOSFETs earlier, you will see that.
Okay, sir.
Yeah. Okay. So thank you guys. All the best. See you on Friday then.
Thank you, sir.